PageRank algorithm in big data. Preface. Content of this lecture. In this lecture, we will discuss PageRank algorithm in big data using different framework with different ways and the scale. Let us consider the big graphs. So, in the social scale graph, you can see 1 billion of vertices and 100 billion of edges. So, vertices represents the set of people and the edges represents the relations. So, in a social scale graph, so billion of people are interacting with each other. Therefore, the social scale graph consists of 1 billion vertices and 100 billion edges. In a web scale graph which contains the web pages, as the vertices are much more than the number of people which are there in the universe, hence 50 billion vertices, that is the web pages, are there in web scale graph and 1 trillion edges. Similarly, in a brain scale graph, that is neurons in a human brain, is much more than either the social scale graph or web scale graph, that is 100 billion of vertices are there which are neurons, and the 100 trillion edges are the links between them connecting those neurons. So, what is there in these graph is that they are very big size. Therefore, the computation of these very big huge graphs is becoming a challenge, and in this particular part of the discussion we will see how we are going to process and do the computation on such a big graphs. One such algorithm which is quietly which is well used is called a PageRank algorithm, and PageRank algorithm on using Hadoop technology is useful for computation on such a graph of very big size. So, let us understand about this particular algorithm which is now available and which is fairly used in such a big graph in using this Hadoop technology. So, what we see here is that the page rank, which is also called as a ranking of the pages, is very important because the new challenges of information retrieval on the World Wide Web is there, and it is very common in use in most of the applications and the services. So, which considers a huge number of web pages, that is on the World Wide Web, that is 150 billion by 1998 and 1000 billion by 2008. So, this particular graph which is considered for this computation is going to be very huge and big. So, diversity of web pages varies between different topics, different quality and so on. Now, let us see what do you mean by PageRank. PageRank is a method for rating the importance of web pages objectively and mechanically using the link structure of the web. Meaning to say that the World Wide Web, if it is represented in the form of the graph of web pages, where the pages which are linked to each other, which are referring to each other, are having the link. So, now the page which is being linked by most of the other pages is going to be very important page, whereas the other pages which are not that much linked by the other web pages are not that important. So, the method for rating the importance of web pages using this link structure of the web is called as the page rank. So, the history of the page rank can be traced back. So, the PageRank algorithm was developed by Larry Page and Sergey Brin of Google. It is the first as part of the research project about the new kind of search engine where this PageRank algorithm was used. That project started in 1995 and led to the functional prototype in 1998. So, let us see that using this particular picture. So, the pages which are very important are shown with a bigger size compared to the pages which are not that important, shown by the smaller size. Now, the page rank is denoted by E, let us say. So, the page rank we are denoting by the symbol PR. PR is the page rank of the page E. So, this page rank algorithm will give the pages the ranks, the scores based on the number of links which are pointing to it. For example, this particular page which is shown as a very fat node, you see that most of these links are pointing to it. Therefore, the size or the rank or the score of this particular page is higher compared to the all other pages where not that many number of links are pointing to it. And if this particular fat page is pointing to some other web page, then that page also get more importance. Hence, this kind of ranking is computed through an algorithm which gives the ranks to the pages, or this is also called as a score, which is fairly based on the number of links which are pointing to them. So, the number of links from many pages will indicate that it is a very high rank web page or it is an important page, and the links from a high rank page is also going to be contributing to a high rank. So, considering these two aspects or the rating into the algorithm, the PageRank has combined these two different notions to give the rating or the score to the web pages. Now, let us go in more detail of an example. Let us say that node A is pointed by all other nodes, that is B, C, D. Now, then in that case, the initial page rank here, there are 4 nodes. So, initial page rank is equally divided 1 upon 4, that is 0.25. So, 0.25 is given the initial page rank of every page, that is the initial page rank is equal to 1 upon 4 for all the nodes, because the total number of nodes is 4, and let us say that initially it is to be divided 1 by 4. So, 0.25 is the initial page rank. Now, these values are to be given back to the page rank. So, page rank of A will be recomputed again in the first iterations. So, after completing the first iteration, the page rank of A will be recalculated in this manner. So, for example, if let us say B has also added the links to A and C. So, the page rank of B, that is 0.25, will be equally divided into 2 parts, and this page rank will be given back to C and A. So, if we calculate it in this manner, and the page ranks values which are calculated, which is iterated in each iterations in this particular manner. So, page rank value is given by this particular formula, where each page, for example, page A is pointed by page B, page C, page D, and so on. So their page rank divided by total number of outgoing links which are there, it is to be divided into equally, and that is to be multiplied by the damping factor. Plus this 1 minus d upon n, n is the total number of pages. So this particular way the page rank is calculated using this particular formula, where P1, P2 and so on, Pn are the pages under the consideration, and row P is the set of pages that link to the P, and LP is the number of outbound links on page P, and n is the total number of pages. Now this particular after the fixed number of iterations, or when the convergence is assumed to be a very small value of changes, then the execution of the PageRank algorithm converges, and the final values of the PageRank will be the PageRank of those algorithms. So in summary, the PageRank is the first algorithm given by the Google search engine to rank the web pages in their search engine results. So we have shown how to calculate iteratively the PageRank using a formula for every vertex in a given graph. Let us see how MapReduce can be applied to this PageRank algorithm, so that a large scale graphs we can apply this algorithm PageRank on a very big size graphs. So PageRank MapReduce applied on a PageRank has two components. One is called mapper, the other is called the reducer. In the mapper phase, we have taken the input as the node IDs, and so it is the vertex ID, and this is the vertex for which we are going to calculate the PageRank. So for a vertex n, what we will do here is that we will find out, or we will consider the current PageRank of node n, and also we will find out the total number of adjacency list, or the total number of neighbors of n. So this particular PageRank will be divided by the total number of neighbors, that will be calculating its PageRank. And then for all values of the node IDs m in its neighbor list or its adjacency list, it will emit these values of this ID m and the value of p. Now as far as the reducer is concerned, after getting these values m for the node m, all these values when it is collected, that is PageRanks from all its neighbors. So let us say that this, when it collects the PageRanks from different P1, P2 and so on up to. So these PageRanks when is being sent by the map function, and when it is received at m, then the reducer will now calculate the PageRanks. So it will start with m is equal to null and s, the calculating the value of PageRank in s variable. So what it will do is for all p values which are there receiving the PageRanks, and if it is not a vertex, that means if p is not a vertex, then it is the PageRank which is being sent. So basically it will add the value of s to p, and the PageRank will be calculated based on the PageRank is equal to s divided by 0.85. So 0.85 s multiplied by 0.85, 0.85 is a damping factor. And the other portion where you have to add 1 minus d upon n. So n is the total number of vertices, and 1 minus d, that is 1 minus 0.85, it becomes 0.15. So this will be the total summation of these two will become the page rank of nodem, and it will be emitted from the reducer function m and vertex id. Now there is one more function, one more statement which we have omitted, is that this not only will send the page rank of the neighboring node, but the node itself as the complex object will be emitted out here in this algorithm. So it will emit n and vertex n. So here it will be checked if p is the vertex, is p is the vertex. So if p is the vertex, then m will be added to the p. That means it is the complete complex node object which is being emitted out of the mapper, not the page ranks. So both of them are being used. So p is the complex object is the state variable which are also transferred or emitted along with the page rank value. So this was the MapReduce for implementation for page rank. So here let us see the problems in this implementation of a MapReduce version of a page rank. Here we have to see that entire state of a graph is shuffled on every iteration. State in the sense we have seen the node object as the state variable also is along with the page rank values also is being communicated. So we only need to shuffle the new rank contribution, not the entire graph structure. So this is the problem of internal implementation. So in a newer versions like Pregel, then Graph Lab or Giraffe or GraphX has given a concept of the internal implementation of the iterations of a graph. Hence the transferring of the entire state during the shuffle is not required. Therefore more efficient versions are now available instead of this implementation problem which we have just seen. Further, we only need to shuffle the new rank contribution, not the entire graph structure. That we have seen that in the newer framework of a graph computation, this is resolved. Further, we have to control the iterations outside of the MapReduce. Let us see how the Pregel, the page rank, is implemented. Pregel is originally from the Google. It is an open source implementation. The other such open source implementation which are available called Apache Giraffe and standard GPS, then JPregel and Hama. Batch algorithms on the large scale graph processing, it is being used, the Pregel. Now let us see the iterations in the Pregel. So Pregel doesn't use the MapReduce notion of the concept which we have seen in the previous slide. So here in the Pregel, the entire vertex is being programmed, only one vertex program is written, and here we have to see for any vertex which is active, or if the maximum iterations are not reached, then for each vertex this particular loop will run in parallel. What it will do in this iteration is that it will process the messages from the neighbors from the previous iterations. So this is required. Why? Because it will bring the page ranks from the neighbors, and then it will send the message to the neighbors and set the active flag appropriately. So what it will do is it will collect, it will receive the messages of the previous iteration and compute or update the new page ranks, and then again send the message to the neighbors about the new page rank, and it will set the active flag appropriately. So that means when a particular node is not doing any of these actions, then the node is not active, it is passive, and it will be out of the action in the further iterations. So let us go and see the detailed algorithm of PageRank in the Pregel. So here we have we see that it is a super step. Super step means this is the iteration of the PageRank algorithm on a particular vertex or a node. What it does, it will initialize the value of sum, and it will collect the messages, the values which comes into the messages, and then using this particular summation of all the values of the PageRank which it has collected, it will apply the damping factor, that is 0.85, and then it will calculate 0.15 divided by total number of nodes, and this will be the new PageRank. Now, if this particular number of iterations is less than 30, and then it will that means it is not terminated, still it has to send the messages. So it will send the messages to all the neighbors and send to all the neighbors divided by n. Why? Because the PageRank will be equally divided across all the outgoing edges, and this particular iterations will keep on repeating, and in the end it will vote to the halt if no action is being taken. So this is the vertex program of the PageRank in Pregel. You see that it is not becoming complicated as you have seen in the MapReduce. So a vertex program we can write down, and which will calculate the PageRank in parallel of all the vertices. In the graph. So the parallel graph execution for this particular code will run on all the vertices, and they will calculate the PageRank over iterations, and once the iterations finishes, that is, it converges the PageRank, and it will be the value. So this is the PageRank implementation. Let us see the example of this algorithm and this approach. So this is the initial condition. So initial PageRanks of all the nodes will be, so there are 5 nodes, so 1 upon 5, that is 0.2. So 0.2 will be the initial PageRank, and that is 1 upon 5. It is given to all the nodes. Now let us see that this particular node has two outgoing links. So hence so it is 2 outgoing links. So basically the share of the PageRank which will go around this ring is 0.2 divided by 2, that becomes 0.1. So 0.1 and 0.1 will be the contribution of the PageRank on all these links. Similarly here 1, 2, 3. So 0.2 divided by 3, 0.2 divided by 3, 0.2 divided by 3 will be the PageRank which will be sent along that link. And here 0.2 will be there is only one outgoing edge, so the 0.2 divided by 1, and here also 0.2 divided by 1, this is there. Now as far as this node is concerned, let us consider this node. So what it does is it will calculate the sum of incoming PageRanks, that is 0.2 divided by 1 plus 0.2 divided by 3. And then it will multiply by 0.85, that is a damping ratio, and plus what it does is that it will add 0.15 divided by total number of nodes total number of nodes is that is 3 here in this case. So in this manner the incoming so basically you can see here the value will become 0.426 over here, and this is 0.1, and why these values are changed is because this contribution is 0. So 0.15 divided by 5 will become 0.03, and this is the iteration number 1. And in the next iteration you see that these two values are not changing in the next iteration. So these two values are not changing in the next iteration, so they will become red. Red in the sense they will stop participating in the further iterations, and these values have to be which are sent by these nodes earlier, they will be stored in the buffer, because in the further iteration they will not participate, but these values are going to be fixed and a constant which is going to be used. And you see that here now in this iteration this particular node is out of the action, so it will be not active, and finally at this stage the PageRank algorithm will terminate with these values. So in conclusion, graph structured data are increasingly common in data science context due to their ubiquity in modeling the communication between entities, that is the people in the social network, computers in the internet communication, cities and countries in the transportation network, and the web pages in the World Wide Web, or the corporations in the financial corporations. So in this lecture we have discussed important algorithm, that is a PageRank algorithm for extracting the information of the big graph data using the MapReduce and using the Pregel paradigm. Thank you.